Hi everyone, welcome back to Calculus. Today we're going to be working on some related rates word problems. And so just reminding you guys to do related rates problems, the first thing you want to do is you want to draw a picture of the situation. You want to make a list of all the numbers that are given and the rates, figure out which ones are constant. Then you can write a formula for all that, substitute in anything that's unchanging, take the derivative using implicit differentiation, substitute in what you know, and then solve for the measurement or rate that's asked in the problem. Now, if you are following along in your notes packet, we can pick up on page 82 because that's where we're going to have some word problems. So our first word problem is about a ladder. So I've got a GIF here of a ladder sliding down the wall, and this is actually a really famous calculus problem because it does set up nicely for us to look at related rates of a triangle. A right triangle uses Pythagorean theorem. So I have an animation here to give you a better idea of what's happening. But here's the problem. We've got a 13-foot ladder. It's going to lean on the wall like what this guy's doing. Obviously, this is not a good idea because he's falling. So be careful when you use a ladder. But a 13-foot ladder is leaning against a vertical wall. If the lower end of the ladder is pulled away, like right there, okay, at a rate of 2 feet per second, how fast is the top of the ladder? So how fast is the top coming down the wall? At the end, so the top is 12 feet above the ground in this case. So we're going to do part A, but we're not going to do part B. So you can mark off part B. Okay, so now that we have, take one more second to get a better idea of the situation because it's going to be distracting. So we're going to pull it out. But we've got the ladder sliding out, and then we're also going to be looking at the rate of the speed of the ladder coming down the wall as well. Okay, so let's look at this problem now. Okay, so the first thing I'm going to do is I'm going to draw a more mathematical picture. So we have a triangle happening, right triangle. Okay, and it says that it's a 13-foot ladder. So that means that this hypotenuse of my right triangle is my 13-foot ladder. And the 13 feet, that ladder is not going to extend or shrink. So that 13-foot ladder is a constant measurement. That's not going to change. It leans against a vertical wall. If the lower end of the ladder is pulled away, then we want to know the rate that the ladder is coming down the wall. So we need some labels here. Let's label the bottom X because it's a horizontal measurement and the top Y. And if you look, we've got a right triangle. I need a formula that's going to tie everything together. How about the Pythagorean theorem? So I can do X squared plus Y squared equals 13 squared. I'm substituting in 13 because that 13 stays constant. Now I'm going to go ahead and label all the other rates that they're giving me. It says if the lower end of the ladder is pulled away at a rate of 2 feet per second. So if this is pulled away, that means this distance is increasing at a rate of 2 feet per second. So we're going to say dx dt equals 2 feet per second. Then they also tell me, or they want to know, how fast is the top of the ladder coming down the wall. So the ladder's coming down, so that means this, how fast is that top of the ladder coming down the wall? So they're asking me for this rate of change of y with respect to time. And the other thing I want to note when I find my answer, I notice that if the ladder is sliding down the wall, the length of y is getting smaller and smaller. So this should be negative because the length of y is going to be shrinking. So just a note to myself, should be negative when I get through everything. That's the way I can check myself. What else? At the instant, the top of the ladder is 12 feet. So they want to know what's the rate when y is 12. Okay, so I'll label y to be 12. Now this y equals 12 is not constant. It changes. So that's just an instantaneous moment. So this is not constant. So I am not going to substitute 12 in for y right now. I'm going to substitute it in after I take a derivative. All right, so I have a formula that ties everything together. Now I'm going to take a derivative with respect to time. So I have 2x dx dt plus 2y dy dt equals the derivative of 13 squared is just 0. From there, I'm going to substitute in everything that I know. So let me just bring this up here so I have more space. So I'll have 2 x. I don't know x, but I can find x because when y is 12, I can use the Pythagorean theorem to figure out x. So x, let's see, Pythagorean theorem, x squared plus y squared equals 13 squared. So x would be the square root of 13 squared minus 12 squared. So x would be, yeah, the square root of 13 squared minus 12 squared would be the square root of 25, and the square root of 25 is 5. So this would be 5. But again, the 5 is going to change, 12 is going to change because the ladder is sliding, so these distances are changing. All right, so substitute in the x, so substitute in 5 for x. dx dt, they told me is 2, plus 2y dy dt, so 2, y we said is 12. dy dt is what we are solving for, equals 0. And then from here, it's just an algebra problem that I need to solve for. So 2 times 5 times 2 is 10 times 2, 20, plus 24 dy dt equals 0. If you substitute 20 on both sides, I'll have 24 dy dt equals, this is 24, negative 20. So then divide both sides by 24, and we get dy dt is approximately negative 0.8333 feet per second. And your assignment is going to have you round to 3 decimal places. So we will just follow along with that pattern. This is a y. So notice I did get a negative answer, and that means that this length or the ladder side is decreasing at 0.833 feet every single second. All right, our next example involves a rocket launch. So I have a GIF of a space shuttle launch here to kind of get an idea of the situation that's happening. We have a camera that's mounted 300 feet from a rocket launching pad. The camera is going to need to swivel as the rocket is launched to keep it in focus. The rocket is rising vertically at 800 feet per second. When it is 4,000 feet high, how fast is the camera to rocket distance changing? So in order to keep the rocket in view, this camera is going to have to pivot and look up at that shuttle at a certain speed. Now, we are not going to do part B. We're only going to do part A, and that deals with how far is the distance from this rocket to the camera changing at every second. And it's actually going to be pretty fast. So let's look at this. Okay, so we've got a camera. It's mounted 3,000 feet from the rocket launching pad. I'm going to go ahead and label that 3,000 feet. So from here to here, let's label this distance x. It's 3,000 feet. Now, this 3,000 feet, this camera is not going back. It's only swiveling. So this 3,000 feet is constant. That does not change. The camera needs to swivel as the rocket is launched to keep it in focus. The rocket is rising vertically at 800 feet per second. So the vertical distance is changing. And it's telling me that the rate of change is 800 feet every second. So dy dt, the rate of change of the vertical distance with respect to time, is equal to 800. And then it's concerned about when it's 4,000 feet high. So at the moment when the rocket is 4,000 feet in the air, how fast is the camera to rocket distance changing? So let's call this distance z. And they want to know the rate of change of the distance between the rocket and the camera. So they're asking me for dz dt. So I have a picture drawn. I've labeled everything they gave me. Again, we're not going to do part B. So let's start coming up with a formula that can relate x, y, and z all together. Since this is another right triangle and I'm dealing with the length of each side, I'm going to choose to do the Pythagorean theorem. So x squared plus y squared equals z squared. X is constant, so I'm going to go ahead and substitute in that 3,000. 3,000 squared plus y squared equals z squared. Let's see, nothing else. The vertical distance changes because the rocket keeps going up, and since the rocket keeps going up, then the distance from the camera to the rocket also changes. So y and z change. All right, now go ahead and take a derivative. Derivative of 3,000 squared is 0. Plus derivative of y squared is 2y dy dt equals derivative of z squared is 2z dz dt. And I see I'm going to have to substitute a value in for the y, which I don't have yet. Dy dt, I do have. Z, oh wait, it says when, oh yeah, I do have y. There we go, do have y. Dy dt, I've got dz dt is what I'm trying to find, but I do need to figure out what z is. So I can find z with Pythagorean theorem again. I can say 3,000 squared plus y squared equals z squared, and then solve using Pythagorean theorem. And we said y would be, oops, need that eraser. What is y? 4,000 right now. So 3,000 squared plus 4,000 squared equals z squared. And when we solve, we end up getting that z will be the square root of, oh, something, so z is going to be 5,000. All right, so now I have all the things I need to substitute in. Let's substitute in what we have. 2 times 4,000. Dy dt is 800 equals 2 times z, which is 5,000, times dz dt, which is what we're trying to solve for. All right, 2 times 4,000 times 8,000 is 64 million. Yeah, 64 million. Equals 10,000 dz dt. Divide both sides by 10,000. And we get that dz dt equals 6,400 feet per second. So every single second, this rocket is getting 6,400 feet further away from this camera. And then as you're working on your assignment, you'll have a problem similar to this, but it's the one about Charlie Brown flying a kite whenever you get to it. So you might want to make a note. Look, so when you get to Charlie Brown flying a kite, look at this one. All right, if you flip the page on your notes, you'll see on page 83, there's a question about two cars that are riding on roads that meet at, and your paper says a 90-degree angle, but we are going to say, sorry, your paper says 60-degree. We're going to make it say a 90-degree angle, and we're actually going to modify this question in your notes quite a bit, just so that it looks a lot more like the one on your assignment. So it says car A is 3, we're going to mark off is 3 miles. We're just going to see how far it's traveling. So car A is, and it's just going to say traveling 40 miles per hour, while car B, and we're going to take away the other information, again, so that it looks like the example in your assignment. Car B is traveling 50 miles per hour. How fast is the distance between the two cars changing if they're both traveling away from the intersection? And we're only going to do part 1. We're not going to do part 2. So in this image, if you pay attention to this car and the blue car, those are the ones that you want to pay attention to, because we've got two cars that are traveling in opposite directions for at a 90-degree angle. So if I connect these two lines, we get another 90-degree angle, and they're traveling in opposite directions. So we have two cars riding on roads that meet at a 90-degree angle. Car A is traveling 40 miles per hour. Car B is traveling 50 miles per hour. How fast is the distance between the two cars changing if they're both traveling away from the intersection? And then we need to add after 2 hours. So after 2 hours, how fast are they traveling away from each other? Yes. Okay, so let's draw, looks like we're going to have a triangle that is formed. So I'm going to draw a triangle over here. It's a little more stationary. Lots of triangles today. So I'll label the horizontal distance X, vertical distance Y. Notice X is going to be increasing because that car is constantly moving. Y is also increasing, this car is moving, and then the distance between them is also increasing. So nothing is constant here. Let's call the distance between them Z. Car A, which is down at the bottom, is traveling 40 miles per hour. So that tells me dx dt is going to be 40 miles per hour. Car B is traveling 50 miles per hour, so dy dt equals 50 miles per hour. And they're asking for dz dt after 2 hours. So we are adding the after 2 hours because that's what comes up on your assignment as well. And notice I eliminated this earlier information. We'll need that too. So first, if I start off, if I write an equation that relates x, y, and z together, I can use Pythagorean theorem, x squared plus y squared equals z squared. Okay, nothing changes. Everything changes. So I can go ahead and take a derivative, 2x dx dt plus 2y dy dt equals 2z dz dt. I'm going to have to substitute an x and a y and a z. So I can come up with the x, y, and z values by taking the information about it being after 2 hours. So let's see, after 2 hours. So I've got car A. So if car A is traveling 40 miles per hour or 40 miles every hour, then after 2 hours, it should have traveled 80 miles. So I'll label this 80. For car B is traveling 50 miles per hour every hour. So after 2 hours, and it says 8, after 2 hours, car B should have traveled 100 miles. So I'll label this part 100. And then I can use Pythagorean theorem to find the z value. When you use Pythagorean theorem, you end up getting that the z is the square root of 16,400. All right, so it's like taking all of that, the 100, the 80, the square root of 16,400, all the values for dx, dt, dy, dt, dz, dt. We'll substitute everything in. Draw a line so it's not all. Yep. All right, so I'll do 2 times 80. So substituting everything in, 2x was 80, dx dt was 40, 2, and then y was 100, dy dt was 50, equals 2 times z, which was the square root of 16,400, and then we are solving for dz dt. So now we can combine using algebra. Combine algebraically, you get 6,400 plus 10,000 equals 2 square root of 16,400 dz dt. When you solve for dz dt, you'll add these two together and then divide by 2 square root of 16,400. That'll make dz dt be approximately 64.031 miles per hour. Every hour, the two cars are getting to be about 64 miles further apart every single hour.